here. Yeah. Okay, there's John also. Okay, John, I was already jumping in doing this little presentation. So I'm actually recording it just in case. That's good. Okay, good. So I think you should be seeing my screen now, right? Yeah. And so what emerged from many different attempts to teach this, DFT is a survey over essentially all the modules, small little pieces of teaching that is reflected in the different talks we have. In my slides, it's actually different sets of slides. And the goal was actually to make little individual videos about these different modules. And it's also an interesting issue about the logical structure of DFT as we now see it. And there has been some shift in how we present DFT in the summer schools compared to our book, let's say. So here I just had the keywords, and I was going to discuss that a little bit with you, and then also collect maybe additional modules that are already there that some of you do in your teaching that could be added. I did add some, but there's more. I know that I haven't, for instance, I haven't included some neuromorphic modules and other things. The second sort of topic is to talk about the relationship between DFT and other areas, other fields. And I have a module that I teach at these events that is much more differentiated than it was in the past. And again, they're just the keywords here. And I was going to go through that with you and maybe also add ideas that you have about such modules. So everything that I have here is sort of substantiated by having some slides or having taught it, or some information like that. Some of it are presentations others have made that some of you have. So I thought that I would go through these. Some of those are fairly obvious to you all, and then some, discuss those that are maybe more novel or maybe that need discussion. Good. So this is the rough way I organize this. So there is foundations of neurodynamics and foundations of neural fields, as a new chapter, foundations of neural architectures, and then it goes sort of to higher level stuff, namely multidimensional fields, learning rules, advanced forms of dynamics, and then different interfaces. So these are sort of more specific models for certain things, and then sample architectures, and ultimately something about motor systems. This is not complete necessarily.
Can I ask a question, Gregor?
Oh, please.
Kind of curious. So looking at what you have here, I can see ways in which it's actually similar to the book.
Yes.
But then you highlighted ways in which it's different. Can you maybe give us a sense of what some of the key differences are in your mind?
So there are extensions over the book as we go ahead. That's, of course, that's an update. The key difference, I would say, over the book is to have a slightly different discourse about how the dimensions come about. And in fact, in the latest version, and this is sort of the first 2 points here, so this came about in 2 steps in the history. One was that I very often realized that when we were teaching this, that it was a bit of a magic thing that we're talking about. This is the field over color, or the field over visual space, and things like that. And without really, and that's how we do it in the books as well, without really saying, how come, how do you get a field like that? Why is a particular population, the brain, a representation of that? And of course, in the back of our mind was always this idea, is because of how this population is connected to the rest, to sensory input and output. But that was, I would say, not emphasized very strongly, or maybe not made very clear. And that reflected, I think, also the history of how we did it in DFT modeling. And if you think back to the A not B model, let's say, with Esther, then we just wrote down that model, right? And the inputs were Gaussians, but we didn't really say exactly how these inputs come from the sensory surface. It was ultimately when we did robotic models that we had to specify that, and over time, this was elaborated. And I think that has been a source of misunderstanding, and maybe it reflects also how connectionist models originally were. They also just wrote down a note that stands for a letter. and didn't really say how that comes about. So in the first step, I started to teach more about that. I noticed my students struggle with that, and then I started to emphasize the way dimensions come about by the forward connectivity. And in the second step, I actually changed this discourse a little bit, and this was something that happened when I mean, I actually might misremember, but in my recollection, it happened when we wrote this chapter with Daniel recently for a book. No, it's for a special issue. Actually, no, Daniel isn't here today. And in that chapter, we actually talked about the single neuron interaction, self-stabilization, the instabilities, and then just said, to generalize this to populations, we need some form how interaction it creates local list representations, peaks of activity, local populations that stand for something. And we talked about the dimension as just what organizes these interactions. So close means it's like it stands for the same thing. Let's say makes the peak self-excites, and then far means it competes with those things. And what these dimensions were was not actually initially specified. And that's how I'm trying to teach this now. That is, talk about the interaction as the organizing principle, and only then really talk about how sensory information or motor information is related to that organization of the kernel, which I think is scientifically, logically the correct view, even though it's a bit abstract and kind of difficult to do. So in the teaching, I'm actually not doing it quite in this puristic form. I'm just demonstrating field dynamics without having said what the dimension is. And then I talk about how the dimensions come about. And the more general issue of localist representations is then what that actually means. We recently had a meeting in Bochum where we discussed this in more depth after our Norwich discussion about that. And that is a topic of discussion then. It's not really done in the introductory teaching. So that's really the main difference. Everything else is just extension that we have moved so much further, I would say, in the meantime, than we had in the book.
Great, thanks.
Good. So in Neuro Foundations, other subtle differences, not exactly a contradiction to the book, is that when I teach it, I actually start with a little neurophysics module. I call it neurophysics. It's really arguing about membranes and that they have these properties with electrical charge, and I show spiking and so on, not in any detail, but just to say what neurons are like in the brain. And that is what I use to motivate the minus U term. That is in the the membrane dynamics. You inject a current, you see the exponential relaxation, and that is what the U dot equals minus U models. And it's from that you get the order of magnitude of the time scale, tau even being about 10 milliseconds and 20 milliseconds. And so I give that a little background. We have that in the book in a box, but we didn't really say that that's the reason why we have U dot equals minus U. We had this more abstract Einstein argument, which was always a bit difficult for listeners to understand. And so replace this now by really grounding it this way, and then say that in the limit that we will be looking at, we're not looking at the spiking, we're replacing the spiking by a sigmoid. And that's the activation concept is then defined relative to the sigmoid, and then we're no longer talking about this being an actual membrane potential. So it's this more abstract activation variable. So that's what this neurophysics foundation module is. It's very short. It's like a couple of slides module. And then the second one is what they're all familiar with. That's, I think, the first book chapter we have with, which I wrote with Hendrik, and I don't know, maybe just with Hendrik. This is the one with, U dot equals minus U plus resting level plus input. And you look that input is just lifting up activation and down. How time courses then are just low pass filtered and so on. And then part of that is, this is all just one lecture in my case. It could be separated maybe into two little modules, where these first two would be one, And then the other two are what you're familiar with, is self-excitation, which makes the detection instability in the single unit. And then the other one is two inhibitory neurons that make selection. They're very logical, because if you have two neurons and you couple them excitatorily, there's nothing additional over the single neuron. It doesn't do anything different. And then we say, but a different comes when they're inhibitory. So they have all these instabilities. And then in my teaching, I actually do then the fields right after that. That is, say the fields. So I just write down the kernel of interaction and say we have this comparison that now we have a dimension. And along that dimension, you shift from excitatory to inhibitory. I use this graph we have in the book where we say the discrete ones were just sampling this field. So if one neuron was in one location, remember we have this graph with the gray shade where around one region, and then there's another gray shade around another region. If that's far enough, it's inhibitory. And then just say then there are all these different instabilities, includes the simulation, all the instabilities, detection, selection, memory, and the boost-driven detection. And with the one point that can be made there is sustained activation. In the single neuron, it's not really so easy to say what that means. But if you have a field, then you can say that sustained activation is when you're not going through the reverse detection instability, either though the localized input is zero. Because in the field, you can make a distinction between localized input and global, like resting level input. So that is all just about neurodynamics. So at this point, you haven't really defined the field dimensions. That's actually, I do that teaching now in this form.
Yeah, can I
yes, please
make one point? I think actually one thing that may sometimes be hard to understand or to fully grasp is this time continuous property, or actually the how we conceptualize these neurons as or the models as continuously running, which is quite different to a lot of connectionist models and a lot of general models that get some input, do some processing, and then produce an output.
Yes.
And I think that is one thing that is important to kind of point out early on, and probably best with some kind of example, which of course then probably depends on the kind of audience that you're trying to reach. But I know.
I recognize that in the neurophysics module, I have this argument that in real neurons, the membrane potential is continuous in time. It's just physically. And then spiking events are these discrete events. And then I argue, but these are not really clocked. It's not like there's an discrete update cycle, but they could occur at any time. And in that sense, within a population or across time, they sample continuous time.
Yeah, that is the time continuous part. But actually, my comment was more about is that our models are intended to be just operating continuously, like robotic, like this kind of looking models that, of course, in practice, when we do model physical experiments, we still have trials, and the model starts in some state and then runs until some point.
I see.
But that's really kind of an artificial organization into epochs that we also impose on the model, but this idea that the model is just always operating, that it doesn't start at some point.
Yes.
And I think that is
really interesting. That's part of this autonomy idea that they're always operating.
Yeah, I know.
I was just gonna say I completely agree with Sebastian. We ran into this in the this auditory stuff we're doing now, where of course sampling auditory information through time is a big deal, and none of these models are continuous in time. And it's always, there's at one extreme you've got input, process, output, but even if have a connectionist model that has some recurrency to it, it's still operating over a small window of time always. And to generalize that to a model where it's just this continuous operation through time is I think almost revolutionary to some people in some people's minds.
Yeah, that's
Yeah, and I think it's not that easy to grasp for people who are used to this kind of
Yeah.
model that kind of starts at some point, gets an input, or just starts when it gets an input and then produces an output, and then it's done.
It's a very good point. I really appreciate that. It's so it's different from just time being continuous. It's this
Exactly.
continuous
It's really more
operation. So there's a problem when one teaches that, which is that the audience, especially the younger people who come to our workshops, are often somewhat naive about that, and it's not easy to to distinguish our approach from other approaches because they don't even understand those so well. For instance,
I guess that's true. That there's so I was more thinking about people who do have some expectations and some kind of.
So, for instance, this module, the other module about comparing DFT to other approaches, is something that I always wanted to do in the introductory class, and it was never successful. People were not really so interested in that, and I think it's really because those people don't have that background. But I do think it's very important for our communication with the scientific community. And so I would even attempt to put that point that you just made as a separate point into this discussion in relation to other approaches.
But I think just I agree with Sebastian that there might be, if you could convey some intuitive sense of what type of neural dynamic model you're after up front.
Yeah. I think that's also
creates that intuition.
Broader issue that I mean, of course, as I said, starting with an example of what kind of model or what a model that we are building does. And I was thinking of something like these looking models, maybe even a robotic version of that just kind of reacts to salient stimuli and makes eye movements or something. I'm biased by what I'm working with, but that's kind of an example that I can think of that really conveys this idea of a model that just operates.
Right.
And Kulve actually made a similar point. He produced a video that I was supposed to use about an arm moving around. That was trying to make that point. And now I think I didn't quite get it. Now I see that something like that. Yes, it's actually a really good idea.
Can I add a little note?
Yes,
from
please.
the neuromorphic perspective or hardware perspective or implementation perspective? So one needs to be kind of careful in arguing for such models, because when we in the end run these models on a computer and we have to implement them, then in the background running continuously is a dangerous concept, because then so what does it mean? So I need to constantly compute even if the model is doing nothing, which is I think true on conventional computing platform, like on digital von Neumann computing architecture. Now we have the sequential processor. Even if everything is subthreshold, I always have to compute. So that's why our models are potentially heavy computationally. And I think they kind of come into clash with the computing paradigm naturally, because computing paradigm does have this input-output thingy and kind of clocked processing, sequential processing.
Yeah, that's true too. It's a bit ironic twist in that that would be as viewing now neural dynamics as computation, and then of course you don't want to compute. It's also true about subthreshold stuff, which you don't really want to compute, and spiking is actually one way of how to make sure you don't have to do that.
Yeah, and there one can go to the whole neuromorphic story that we need to rethink the concept of computing and kind of even how computing hardware is organized, because today's computing hardware was not built for these type of models. So we kind of as a field need to discover our GPU, like the conventional neural networks, they discovered the GPU as the traffic platform.
So two responses to that. One would be that there are neuromorphic scenarios where this is appropriate. For instance, if you think of these insect-like applications where you would have like a drone or something, that is done this way, then of course you would do that continuously because it's flying and getting sensory input all the time. We just had Cora visit us, who's now with Barbara Webb in Edinburgh, who actually referred to you, Julia. Apparently your work is known there, and you become aware that that's very much this kind of use of neural network that continuously works because the animal is continuously behaving. second point is that I think this could also be something more for discussion, in the sense you have to address people who know that, who have that framework, who think like that, and then you have to say, well, how it relates to that, and perhaps the discussion points are really then targeted to particular audiences. So maybe there might be a need to have a discussion module of saying, okay, if you're interested in computation, then these are the points about DFT. Versus if you're interested in mathematics, psychology, or if you're interested in, I don't know, neuroscience and so on, to have these targeted pieces of discourse about that.
Mm-hmm. Yeah,
and there would be solutions, right? If I have computation implementations, I could deal with problems like that, like have an algorithm that doesn't compute when there's no input, but that is sort of an artificial external implementation thing.
Yeah. So in today's neuromorphic hardware, the solution is that the subthreshold computation, it is done, but it's cheap.
Yeah.
And only the spike, so suprathreshold activity, is more expensive.
Yeah.
Yeah.
So another point I take from this is that especially these discussion points should be really framed thinking about the audience. So what does the audience, different audiences, and what are their assumptions, and then you connect to those assumptions. And so, for instance, computational people would be one audience. Excellent. So this very good points. Think about that. So that's it's one lecture at the moment. In my course, it will be like an hour lecture. And I'm thinking of making 2 separate videos about it. Just the first 2 terms, one, and the rest is one, a little longer one. So that's fairly standard. It's just a slight thing. And now the second thing I do, that is roughly the second chapter of the book that I wrote with Anne, but it is framed now differently, because it's now really about, it's actually mixing the second and third chapter, I should say. It's really now saying, okay, how do the fields come about? And this is about this forward connectivity, either from sensory surface to the field or from the field to the motor surfaces, and it introduces notions like receptive field and tuning with these little drawings and so on. And I sometimes also include here the population code embedding, the motor and the perception version, because that makes the notion of receptive fields and tuning curve explicit, even though it's a slightly different, it mixes topics because it also brings in the population code topic. And that was, of course, what is in the book chapter 3. In the current teaching, do this much more briefly, because we tend to, it takes too long to do all of this in depth, and it's appropriate that there would be more in the book. And another element that I have is that I use the Estela Bishu robot to illustrate the forward extraction, the sensory driven, like the 5 microphones that make inputs forward to the field, as a demo of how these come about. So it's fairly simple. This is essentially it can be 1 or 2 little modules, when I think the neural part could be sort of separate. So actually the more appropriate way is that these 2 are connected, you demonstrate that, and then there is the neural embedding, which is also optional. Sometimes I don't do the neural population embedding in shorter versions. So there's nothing really new here, except for it's separating it out from the field dynamics. And then the next is something that we used to have distributed all over the place. In the book, it's in chapters, I think the 7nov2023 chapter, which is maybe 6 or 7, and in some of Sebastian's chapters, and I don't remember exactly. So now I think it was also in one of our recent review papers that we felt a need to, it's a paper I'm just finding, actually the Jan thesis paper, becomes very clear that we need this. So this talks about how multiple fields are connected into architectures. And so a very simple thing, that they project onto each other, right? And this introduces the notion of a projection kernel, so that you have some homogeneous projections. So this can be from one dimension that is somehow in a one-to-one relationship to another dimension, kind of like being a copy of the same dimension, a different spatial dimension, for instance. Or it can have that feature of compression, where you integrate out one dimension, or it can have the property of expansion, where you, give a ridge or slice input and so on. And that is illustrated more concretely. It makes more sense when you do this for the nodes. So these could be nodes that stand for a region in a space, or the forward connectivity, and it can be bidirectional, has is sort of spatially localized, and that's how the idea of a concept node can come about. And then there's also boost nodes. A node can also so a form of expansion is that a node excites a whole field. And these are things that we use later. So currently this is distributed all over the place, and I think of this as something that could be done in isolation. There is a discussion point that I'm currently always putting in the back of the lectures, but I'm thinking of maybe even introducing it here, in that, this modularity argument. Why are fields, when you couple them into these larger architectures, still retain that meaning that they are, that they are working memory for color, for instance? So that's a functional, ascribing function to a field, both in terms of its function, like being working memory, and in terms of what it represents. And the function is, in our language, connected to the dynamic mode, that is, sustained, for instance, or multi-peak, and so on. That was explained early in the dynamic simulations, or could also be done here. And the contents is the dimension that it is about. And the two arguments are structural stability, that is the fact that we have attractor states, makes that when the parameters of the field change, of the dynamics change, the attractors persist. And that makes that when you couple, but coupling is essentially like a change of the equation, then the dynamic properties are preserved up to a limit. And the fact that it's still, so that's how the function is preserved in the architecture. And the other is what I sometimes call the non-synesthesia principle. Not sure that's spelled correctly here. Which is this idea that within architectures, we just postulate that forward connectivities are not inconsistent. That is, you're not driving one field by color, and at the same time, you have some forward connectivity that drives the same neurons by, I don't know, auditory frequency. So you don't get a confusion of one peak possibly standing for a sound or standing for a color, which is sort of an additional principle, right? One can write down fields that are like that, but we're not doing that because we assume the brain doesn't do that. I think it could be even useful to introduce that early on. So far, I'm always doing that only in a discussion session. That's a part that we never really made explicit, I believe, in our teaching in the past. Yeah, sounds reasonable. Good. So that's all the foundational stuff. And then the sort of more advanced, the next three and the more advanced ones are multidimensional fields. So multidimensional fields, of course, multidimensional is not so important when it's just a matter of, Julia has to leave, which it's fine. It's really important when there are different dimensions, right? So I usually start this by saying, well, if there's no difference between the dynamics in a 2, 3, or 4 dimensional field per se, they always have peaks, they are blobs, or higher dimensional spaces that just localize the activation. But what the difference comes about when the dimensions have different meanings. Like, for instance, if one is color and the other is space. I argue that that is like a joint representation. That is, for every combination of, let's say, color and space, you have a neuron for that. So it's also a costly thing. And then I explain the different operations on that. That's essentially from Sebastian's book chapter, where you can extract by the compression operation, you extract a dimension, and then by the expansion projection, you can bind to contents together. You have no color and orientation, you bind these together. You can illustrate the binding problem, that if you can do this only one item at a time. And the principle of visual search is sort of a combination of these two, right? Where you put in a room and you project out. And that could be sort of shown so in a demo of principle. And the binding through space is then an expansion of that, where you say now you have that shared dimension among multiple fields. And I'm using a picture from another book chapter. I think it's maybe it comes from John originally. Maybe chapter 6, where this toy example with the letters and the colors, and you're saying, which letter is the green one, and so illustrating the idea from that, and sort of postulate that as a general principle. And that's then really the way we use binding, while the first is really the notion of joint representation. So there's a bit of confusion sometimes. We just recently discussed that this binding in the sense of joint representation is a different kind of binding than the binding through space. And then the third example in this domain is coordinate transforms, because in the coordinate transforms, the gain field is a joint representation of the steering dimension and the dimension that's to be transformed. And so I'm also including that in this module. Again, it could be broken up maybe into smaller modules. Currently, this is all just in one lecture. So that gives the foundation for the higher cognition stuff. Yeah, and then there is at some point I always have to insert the learning module. It's not always clear where that goes, because the memory trace is clearly needed, and then I usually have a little like 2-slide summary of the dynamic HEP rule, which I took in this form from Julia's paper. And I have never really done this, but I would like to include the reward modulated HEP rule that we have in the de Kulve model and a couple other places, like in some of Sebastian's work, as a more advanced form of that. And that will be a more interesting. Then one could define autonomous learning from that. Again, this has to be very limited, because to really understand autonomous learning, you need to have the entire architecture that can create experiences. So I'm not sure about that. Okay, so that's the learning module. And then advanced forms of neurodynamics, I don't always do that. So one is to illustrate two-layer fields. We have that in the book. With oscillations in light of neuro work, also really emphasizing active transients. And then the sequence generation mechanism itself. So the conditional satisfaction mechanism is really how to destabilize, have an attractor and then have the attractor end. And it's a separate issue what you do then next, which I now try to actually keep as a separate issue. And I often skip, but sometimes do the 3-layer model. So the change detection model as a special dynamic, just as a dynamic thing. So as a property of dynamics. The generic 3-level architecture, let's say. And then everything else is then more related to substance. So the interfaces to data are sort of the classic examples. So peak generation in sense of decision-making, reaction time, the metric effects and probabilistic effects, the time movement initiations like the Elhagen paper, and then work on visual working memory estimation and change detection. So I sometimes have a Jeff Johnson module in there, and actually I have separated out the developmental things later. And in fact, in my lecturing, I don't separate the developmental stuff is separate. So these are just some illustrations how fields can explain data. I usually don't include the neural data in the same thing, even though that could be done. This is the more elementary thing.
Might be worthwhile to at least have some discussion of I know in the other outline you probably have mathematical psychology in there and
yes,
parameter fitting and things like that, but I wonder if there's some initial discussion of that here would be useful.
Yeah, especially here in this, that's right. And I do have actually lecture slides because I do lecture about different approaches in the cognitive science program. It's actually an interesting idea to combine them in the same lecture. Yeah,
Sort of the general question of what does it mean to fit data?
Yeah. So it could be so in verbal discourse, I sometimes do that. I say, here's a model, for instance, that has properties. The metrics, for instance, are really important to the fields because the fields are, really about that. So looking at metric effects is interesting, while the classical models were more about probabilistic effects, for instance, because it's about amount of information. But it might be actually really interesting to also illustrate this idea. In fact, I would say, the diffusion model isn't really contradictory to DFT. It's almost like it's a limit case of DFT where you just pick out this one little part of it. Now, if you take the Asher-McClelland account, you could say that's just an approximation. And interesting, I've not done it that way, but that might be an interesting way to do that.
I mean, there's also another theme here of like, when you talk about interfacing with data, the advantages of working with a process model to do that. Because you can imagine different ways to interface with data, and with DF models or with DFT, it's ultimately about sort of embedding the model in the task and the scenario, right? And taking measurements on the model in the same way you take measurements on people.
Yeah.
And that then affords a great deal of generalization across tasks and contexts. So
well, John, I think in relation to like our VWM project, explaining both correct and incorrect performance, or explaining different sources of error or things that can arise that lead to deviations, or just rates variations in performance and things like that.
Right. So there's
very interesting topics. In my experience, these ones here are the ones that I use for beginners, like to just illustrate it. What you're hinting at, of course, is much more sophisticated, and I wonder how to actually do that.
Yeah.
Since I have a module on process models then in the discussion. Of course, it's better if it's connected to something concrete.
Yeah.
It's not easy to pull that off, to have to explain it, and then already you need a lot of concepts already to talk about that. So that would be maybe like more for advanced forms of teaching. That's often a problem that we have, that we're very richly connected to existing concepts and approaches, but you need to establish a lot of stuff before you can talk about it. But I took a note, actually, I think there are interesting extensions that we could do. So these are limited. I mean, even in my whole semester course, which is 14 lectures, I don't, for instance, often don't get really to this one, to the visual working memory and all that. I often have only these here.
Yeah.
Okay, then the stuff that's new over the book is the more recent stuff we do in higher cognition. So it's the grounding, object nodes, concepts, the notion of an object concept nodes. I'm typically using, I have one module where I use Matthias Richter's version of this to illustrate how concepts are grounded, how relations are grounded, and how the whole architecture is organized with the different roles, the grammatical roles. I have a related set where we do this for mental mapping. Same architecture does mental mapping. We take phrases and you make a map. And then there's the more recent work, which in our lectures is usually a whole separate lecture, for instance, that Daniel does about conceptual structure and binding through index, which we recently had. And then serial order. Actually, serial order is the more general topic is how you then actually select the next item. And that's where I usually establish the link between our condition of satisfaction machinery and things like gradient approach, the positional approach, and then the chaining approach. I have a few slides about that. And these are the elements that are needed to understand the more complete architectures, or the example architectures where we can do complete things. So currently this is all in one module, but it could be perhaps reorganized a little bit. I'm thinking about that.
And then to connect like this chapter with the data, I think maybe more on the meta level might be interesting to speak about the role of models in science in general. I mean, that's example now for cognitive science or psychology, but it's not too much different, you know, what probably people do when they do climate models. You really need to connect it to data and explain phenomena that
That's
can be
a
observed.
very interesting point. And in fact, this would be maybe in part of this discussion session.
Yeah.
That one could actually even have a more general.
Yeah, I think
idea,
going a little bit more
models in
general and
science.
really how we use models, what we do them for, how we test them, what's a good model.
You know, I actually had I did a lecture in a context like for the graduate school neuroscience, where I talk about different epistemological traditions in physics versus, in this case, was developmental neurobiology. So, you know, law-oriented physics and morphogenesis. Turing's model, for instance, is a model of morphogenesis, but that has never really been very successful in biology, because it thinks about general principles, how shapes might emerge, self-organization, and so on. And then the dominant model in molecular development is sort of information processing, like these molecules that act like keys and have information about gene expression, and they're actually in a sense you know, more information processing. And in that context, it was interesting. There's someone called Evelyn Fox Keller, is a philosopher of science, and she argued that in this field, what people think of field theories are synthesis models. So like climate models, it would be a complete model that takes all the facts that you have and then simulates development, and that would be understanding development as a very different role of a model, right? That's very advanced stuff to get to that level to understand that. Yeah, maybe. Yeah, I'm not sure there's a good audience for that. Good. And so I usually don't teach much about the development. I have a module on the old perseveration model, and you know, sometimes teach about the very simple habituation model. The looking version of it is, I have slides, but rarely ever get there, and I have slides about all of those things. Cognitive control is one of those that I never really teach, but I'm sure Aaron does that. And I have something about spatial position hypothesis. And I haven't really taught about these things, even though I've referred to a simple version of the word learning model with the two label space dimension. I don't know what the keyword for that model is. I took that from one of your papers. And we have evolves, and there are other models here, right? And I think we could generate maybe a sequence of developmental accounts that would be one or two of these modules in a video. I think that's maybe something we could really do on, like, for our DFT webpage, or I know that would be maybe something we could collectively do, or when we do our next workshop, to have a whole set of developmental modules. The developmental, separate that out, because the kinds of questions are still a little bit different in that domain. Yeah, then examples of complete architectures are, I often show the visual search, and scene memory is part of that. We have this serial order architecture, which is not the Julia one, but the one with the pointing. We did, Julia's actually co-author on that. I don't remember. It's Jante Kulve. It's on the table pointing. It's sort of a little more intuitive than the robotic example. I give a lecture about intentional agents as an illustration of, autonomy and things like that. This is Jan Kulve. The grounding are usually it's complete lectures. Like there's a lecture of Daniel's. He has 2 lectures. One is just the Mathis Richter lecture, and that's the Daniel version of it. So in past summer schools, we tied all of those together. So they're the more advanced lectures. They don't explain really the details. They show how the whole architecture works. I haven't done this, but we could do, we have 2 variants of action parsing. We could do that again. We'll have the action phrases. We haven't really lectured about that yet, and that's to be developed. So these are things that we could soon have modules about, I would say. We already taught about the analogy architecture of Mathis Hesse. So there are slides. I did that at some point. And here, I don't think we have any lectures. So that's this direction of synthetic psychology, right? Where we show the function, but we don't really connect to data, and it's not really robotic. And then we have robotic demos. So there's the robotic A0B is a demo I often use. The phonotexis robot of Ersteller itself. Here we have a little we have a paper years ago, and I have a little lecture about that. That's reaching robot with online updating. The architecture is complex, but I'm just highlighting the online updating thing. We have timing. This is also another architecture, catching with online updating. The Julius serial order, I have very nice videos from that, which I use sometimes to illustrate those ideas. And this is the same as above, the Jan Kulve version. And this is what Raul is just developing for in psychonomics. He will have a presentation about that, and the action phrases we actually don't have that yet. And thus I lecture in the summer, and this is something we haven't included in the summer schools typically, about the motor end of things. So remember, in the past we had this lecture about how space code is translated into rate code. This is the special thing with normalization. I've actually kind of dropped that from my lectures because I now think of this being somewhat special and a special trick, even though it does play some role, but I drop it often. And instead now I'm lecturing about neural timers, timing oscillators at time. And we have these demos that Jean-Stéphane Jockheit did and Jan Kulve did. So sometimes this is related to the notion of primitives. I have a whole lecture course about movement generation in the summer, and sort of the neural dynamic variant. It's just some subsets of these are neural dynamic, and one of those is this idea of neural timers. So these are actually all transient, active transient generators that can be turned on and off. And one can talk about coordination in those terms and about behavior organization in these terms. And then there's this whole idea of how time signals like that. So these signals are in rate code, right? When you have generated a time course, it's something that sort of ultimately will be muscle activation. So more firing means, more force generation. So it's already rate code in a sense. And so the transition from space to rate code is really the oscillator. Unlike when you read out the peak, right? That's where you make the moving attractor in a where heading direction is somehow a variable. In the actual animals, there are these head direction cells which are probably similar to heading direction. So the attractor dynamics of these hippocampal guys is perhaps the interface there, and we haven't really elaborated that very well. I actually have a module in my summer semester about that, but it's not really fully neural dynamic. Well, in the arm movement and so on, it's this timing signal that ultimately provides input to the muscles. So the descending pathway is this uncontrolled manifold sort of stuff, the Valère Martin model and more modern versions of it that are, only partially, they're not fully complete. There's no model that combines everything. The Valère Martin model has a non-neural part somewhere in the center. And then there's this work on the muscle models, with the reflexes. And the reflexes are sort of dynamic. They are we have a very simple reflex model. It's just a semilinear threshold thing. And so my latest thing is to combine that all into one architecture as an example. So in summer school, I gave this example, the reaching movement architecture, but I didn't explain all these components. But I'm thinking of trying to present these things in a way that's more closely aligned with DFT principles. So that's where I stand. I think there are other modules out there that some of you guys have developed that would be interesting maybe to ultimately integrate into this.
I guess my question, having seen that survey, it's like I can imagine for the first bits, little 10-minute videos on, having a library that builds systematically the concepts of DFT. But then we get into more and more complex things that are harder to do in short video format and are more like, frankly, 30-minute to 60-minute lectures on particular topics.
Yeah.
So then does it start to almost lose its coherence, or, maybe there are multiple goals here in this module's outline? I mean, I understand this has a history and it came from your course and things like that. So, but just thinking, maybe we want to almost think about it like I felt that there was a natural breaking point where you went away from the 10-minute, here are the basics of DFT videos, to now, here's a whole library of content you could explore depending on what you're interested in.
Yes. So that's absolutely true. Also, in practice, remember in the past, I didn't really have these 10-minute modules, so the difference wasn't so obvious. But there is a difference, and I actually agree with that. So there is so it's a practical thing, and I'm not thinking that we should all the way through. It's not reasonable to do it with these short videos all the way through. I wanted to just get the landscape, but there is also sort of a scientific issue there that we just recently discussed in Bochum, when we talked about localist representations again, and I think we want to iterate that actually here in Bochum again, and that is ultimately, let me put it this way: when we talk about higher cognition, then you would think, well, maybe we just need some additional operators, like some cool operators that do relational thinking and inference and analogy and things like that. And we're concretely thinking about, what corresponds to certain kinds of operators in information processing. Do we have the DFT version of that? Like, the relational, I sometimes call them operators, which just, I don't know, just to allude to something. It wasn't maybe very well thought out. And then I realized it's not really right. I mean, it's not true that we have elementary operators like that, and then we combine things. But it's actually these things that we describe, for instance, as being able to establish relations that is emergent from architectures. And the elements in these architectures are really just the instabilities, ultimately. It's the handful of instabilities. They're just arranged in architectures. Right. And in that sense, there is a real distinction between what the elements are and then what you can do with the elements. And it's not actually true that as we go to higher cognition, we're adding new elements. Right. Rarely, I mean, so I mean, the goal might be to, in the revision, I have to keep working on this, to really be sure what really are elements that we need. Right. And then to also, and to see what all emerges from it. And of course, in teaching, it's not a good idea to just first list all the elements and then show how they work, right? You have to mix these things, but it might still be useful to have organized it so that you've identified what these elements are.
Yeah.
So I think the first modules that you're talking about are the ones where all these elements should be presented. and
Right.
it could perhaps be done in a way where that is a closed list.
Right.
I think it's pretty much the first.
Yeah, so I think
he's from here all this here.
right, and I agree. I think there's probably maybe some ingredients that, with some further thought, could be pulled from the higher cognition section and the development section, and certainly the motor section,
Yeah.
that would add sort of new foundational modules,
Right. Yeah.
that
Yeah.
we haven't seen yet, partly because we're so mired in the current stuff that we haven't taken a step back and said, what are the ingredients here that we're using that have been developed that haven't been almost elevated to the level of a foundational unit, you
That's
know?
right. Exactly. Yeah.
Yeah.
So, for instance, in more recent models like Graul and Mintzberg have that they are using active transients as a timer to run the processes.
Right.
And this is sort of analogous to, I think, what you, John, have done with, I don't remember, with Jeff, or I don't remember, with the same different, where there is a timeout in a sense that one of those, and that is an element. It's a
right.
that's why I'm thinking that the active transient has to be among the elements, because now you have a use of a timer like that,
right,
to make regular switches somewhere.
right. Yeah.
And then there's its role in the motor is actually a little bit different, because that's a tunable active transient. It's a little bit different thing. The other one is where the time, you just have some time for that, but you don't necessarily have to have a precise time. In fact, it's one of the points that you don't need a precise time for it. But then in motor, you need to have those tunable, which does actually make different process requirements. You have to have some softer sigmoid, that is sensitive to levels of inhibition and so on.
Right.
Yeah, so that would be maybe an iteration to further revise this so that it's clearer what the elements are, and then what is done with these elements. Yeah.
And then I guess I also see in the second half, then we need to have some discussion of what are we about with DFT, because ultimately we're moving toward a theory.
Yeah. So this
theory.
other topic, the discussion module.
Because then you have to say, one approach is to just say, here are the foundational elements, and then here's a bunch of examples. But I think we can say more than just, here's a bunch of examples, right? Because all the examples actually fit together into a coherent whole, but we should try to articulate what that whole is that we're pursuing and what the research strategy is.
Yes.
Because we're,
there's the emergence idea that you would say, well, now if you have these elements, you can see how function emerges from structure, from architectures. And then in these architectures, you cannot say that that function is encoded in one of the components, but it is really a property of that architecture. And so
and I'm even thinking about themes of, the arc from going from sensory motor systems to higher cognition, and why pursue that strategy. And
so in my teachings, I sometimes articulate that, but I haven't really found a very good way to do that. I say that the brain is a specific architecture. So it's not a general intelligence. It's specific in the sense that it has, the sensory motor areas. It has principles that come from there, and it has, this non-synesthesia principle means it has specific different discrete representations, and from all of that, those things emerge that we consider to be cognition. And human cognition is specific. We're not actually a very good Google engine, or we're not a spreadsheet. can only do certain things quite well, and those are the
We're
sensory
terrible
motor.
lookup tables,
Yeah, exactly.
especially with aging.
Yeah, exactly.
We can't tell a row from a column anymore.
Yeah.
I just know it was roughly over there.
So
Yeah.
that's an interesting point. I mean, so I haven't really in this, I haven't addressed this in this way. I mean, I have this little thing that I tried out with the neuroscience students. They always hated this, where in the end, I provoked them by saying, so what is a theory of the mind or the brain? Or those guys are more interested.
Right.
And then tell you, give this example that if you had all the data about a brain available, like you have it on a computer, somebody was able to measure everything, because they always complain about lack of
Right.
data. But then you still wouldn't be able to. You have no theory, because if you measure that again on a different brain, everything is a bit different.
Mm.
So a theory would be perhaps if you are finding out which of those brains was based on fraud, on cheating, people not really measuring everything, just making it up. If you are able to identify the brain that's made up, then you know the constraints, the principles, right? For instance, if there is no topography in one brain, then you might see that it's cheating. And so I'm call this the possible brain account. And so DFT could be viewed perhaps as a language in which you are able to write down constraints like that show the properties that all the existing brains must have. And so understanding, what we're going for is understanding these constraints and how from those constraints the functions emerge that we consider to be cognitive or human.
Yeah, no, I can appreciate that, but it sounds like more of saying what the brain is not instead of what the brain is. Like you can rule out that the brains don't. Here are all the violations.
Yeah.
Right, but I want to also be able to say, here's, the structure that has to be here. So instead of what it is,
Yeah, it's I see what you mean. I mean, when you say constraints and it's forbidden, that sounds like that. And maybe that's a misrepresentation, because these models are models, process models. That's the other point. They are really process models, so they can generate that they can generate their behavior. So Raul reviewed a paper that defines what process models are, where people think about that, and I found it somewhat useful. It's very abstract. But then in practice, when I teach, I didn't really go deep into that. And so I ultimately end up just saying it's something like generative models, so models that can really produce time courses of variables that would be generating actual movement behavior, something like that. Which is the more concrete version. They talk about it more abstractly. They're well-defined interfaces to sensors and motors, and they have certain principles that the process account needs to satisfy in order to count as one, but they're somewhat abstract. I don't know, Paul, do you want to comment on that? I looked again at these authors, and I isn't really much follow-up from that, so it wasn't. I don't want to belittle it, but yeah.
Gregor, can you send maybe in somewhere the link to that paper? I'll be interested, because one thing I find very confusing when we speak about process models is that what we in the DFT community might be very different to what the person who, for instance, studies computer science might think about a process model. Because a process model, there is just a diagram with yes, no, and then it's an algorithm which is subdivided in steps. So I think
Yes. Yeah, in fact, these authors
That's a very bad
contemplate,
name in a way.
right? And these authors contemplate algorithmic process models, and they have the abstract way they talk about it. These models would also count as process models. And I think that's not wrong. I mean, our models would be perhaps neural process models in that they have to fulfill certain constraints as well. But in some, you know, if you have a generative neural network model, you know, people could say that's a process model, except that it requires a CPU that, you know, that organizes certain things and so on. But that could be part of what you admit. So we have additional constraints for what a process model is.
I mean, and this could loops back to the conversation earlier about continuous in time and autonomous and these things.
Yeah.
We place a lot of constraint on what a neural process model is.
Yeah, I think so too.
Yeah.
It's really the real time and discontinuities in real time, although it's a continuous model.
Yeah.
That's also very difficult sometimes to grasp.
And that's why in my teaching, I don't really refer to this paper so much, because then there's additional work to characterize what we think of the additional constraints we have on our process models compared to this more abstract notion. But I can appreciate that people who are in other areas of cognitive modeling, for them, this is not so natural. And I mean, even people are kind of close to us still are much more agnostic about exactly what kind of model, what kind of processing element would be allowed. And this paper is an effort to sort of more formalize that notion. So here, maybe just to stop screen sharing. So this is the kinds of things I do in discussing the relationship to other approaches. So already mentioned. So I have three things sometimes to say about DFT as such, namely this modularity issue I mentioned before, neural process models, and propose that it's also some form of neurosymbolics that is attempting to achieve what symbol processing describes, to say how that is actually done by neural networks. In the paper with Daniel, we developed the discourse that it's sort of the opposite of a neural Turing machine approach. You know, Turing machine would be to say, I say that symbol processing is described by some abstract principle like Chomskyan style, or you know, these other guys, I forgot their names, that say you can do you know, rule-based computation and so on, and to say no, that's just a description, but what we need to understand is how the things that look like symbolic processing, that look like compositionality, productivity, and systematicity, how they may emerge from a grounded machine like ours, right? And say that in the effort to achieve that, DFT could be viewed as a neurosymbolic approach. So as an approach, try to emulate that. So that will be different from connectionism in the sense that we're really also interested in the sequence of events that underlie such things that look like simple manipulation. And it's really our sequence generation machinery that does that, while most connectionist models are not really doing that. Right? They're really still primarily doing input-output kind of processing. So that's what I say about DFT as an approach. And then I have modules where I talk about DFT versus embodiment and classical dynamical systems thinking that you're all familiar with. That's more verbal discourse to say, you know, it's the formalization of that, you know, beyond the metaphor. We wrote papers like that. In the relationship to connectionism, the main argument is about localist versus distributed, and this commitment to localist. And we actually iterated that just recently. I can expand on that, but maybe let me just give you the survey. Characterize sometimes the difference to computational neuroscience, so more interested in like principles and constraints than into exact neural implementation, and not necessarily making sense of every neural circuit in the brain. in the relationship to deep networks, which is again based on feed forward versus recurrent very much, and also this autonomy issue. Clarify learning, that most learning in neural networks is actually parameter fitting rather than learning, and then say that we're in autonomous learning. Spiking, you know, this characterization of the population level as abstracting from spiking, and then point out that spiking would be different from population level if spike timing is used in a specific way that's not then within DFT. And then I have a few modules about a real contrast. So this is just always saying that DFT is sort of a limit case, or is some, you know, has some relationship to the others that is not contradictory, while this one is really contrasting. So contrasting to computational models, and that means in this sense of the level Mars sense, you know, computation just describing abstract computational principles versus process model, comparison to R-SOAR and so on, where the function is actually done by information processing. Just in the architectural constraints are just descriptive. It's not really explains, doesn't explain bottlenecks, just puts them in, doesn't explain how they arise. I have a little, with the contrast to these other guys, is a little more specific. And then I have a whole possible module about VSA, which I have stopped doing that because usually nobody knows VSA enough. We've just recently again discovered that VSA, the relationship with, yeah, let's not go there, but this can be discussed, yeah. And how to model in DFT is, I think, an interesting thing for our teaching. We have that in the book, like this chapter 15 on how to model in practice. And I have like a one-page thing in the workshops, and people build a model, and there's a kind of very crude way of talking about that. So I think that's an interesting part of our teaching that we could maybe expand. So I just wanted to throw that out there. I'll put these, send you these slides maybe as in some form, or put them on the webpage so you don't have to worry about remembering them.
So how about like a behavioral and brain sciences that combines all that? So it basically goes through, you know, thinking DFT 30 years on or whatever it is.
Yeah.
And we say, here's what DFT is. Here are the foundational concepts. We make these 10-minute videos, so those are actually linked to the paper, right?
Wow.
And
Yeah.
then we say, you know, some exemplary examples, some examples.
Yeah.
And
Could refer to papers and then have one or two that we actually discuss.
And then discuss how DFT relates to other approaches, and sort of end with what's the vision for DFT? What would the ultimate theory of the
So is
dynamic
BBS
range?
still having these discussion where people
Yeah,
respond?
I think so.
Yeah.
So I thought that's why I thought it would be attractive to get actual feedback. Let's see.
I mean, my
Yeah, it's still a impact factor of 21.
oh, really? Good.
So it's still a real high profile.
So on the one hand, we felt, I think that when we write these papers, like I read a book chapter for a Cambridge handbook and this cognitive neurodynamics on, it's kind of hard to get people to read them.
Right.
But if you force people to comment, you know, it's maybe the
right
of PBS. And some people are sort of specialized in commenting on papers like that.
Right.
That's an idea. Yeah.
And then, you know, it's a expansive agenda for a paper, but maybe that's a good thing because it forces you to be very concise and precise about each section.
Yeah.
Right. And you've basically got the outline of the whole paper there in quite a bit of detail,
Yeah,
right? So still need some thinking to fine tune spots, but I think
Yeah.
that would be a
Yeah.
very compelling
right.
paper and maybe a good way to put it all together in one place.
Yeah.
If we had the videos that you could link to, maybe a
And
good,
the audience, those who would comment on that, that might be an audience who do have grounding in other approaches and would
right,
maybe focus on that point. And so
Right.
and that might be an important way to make it harder to ignore.
exactly. If you put it all in one place, it's harder to ignore. Exactly.
Yeah.
That was my sense as you were going through stuff.
That's an interesting idea. Yeah, so
Yeah.
I definitely think about that, iterate that. My current course is sort of another iteration of that. And my students are, they don't give interesting feedback. It's just you figure, I guess, if it's hard for them, I can see where they struggle. But it's not it's still interesting.
Yeah. But maybe, I mean, if you're interested in the idea, I'd be happy to chat offline and maybe iterate a little bit.
Yeah.
And then maybe we could come back to the group and get very specific feedback on an outline and start to work together as a group on putting something together like
We
that.
can do this like a really large collective paper. So
Yeah, exactly.
So involve a lot of people, and that might also send a message.
Yeah.
Yeah, it would be actually really attractive. Yeah, I mean, it's a lot of work, I'm sure.
Yeah, certainly a lot of work, and
I'll be retired soon, so
yeah.
even though we just decided that I extend my tenure for a year.
Oh yeah.
But no, I still will wind down my administrative part.
That's good. So then you just take all that admin time and you write a BBS paper.
Yeah, that would be good.
Yeah, perfect.
Yeah.
Just a quick question about BBS. It looks like you can submit a pre-proposal.
Yeah.
Yeah,
Is that
that's
something
right.
we want to do?
Yeah, I think so.
Spending too much time on it.
So I think if we could iterate on an outline and a pretty detailed outline based on what Gregor just walked through, that could form the basis for basically a specific proposal. And we can make the arguments of why this is a timely paper and etc.
Yeah, it has to have that. Who's editing this these days? Paul Bloom. Yeah, I think I had Paul Bloom as an editor.
Yeah, he of course knows Larissa well, and I think he would be.
Thanks, Sebastian, for joining us.
Yeah,
somehow I know him. Yeah.
I think he would be receptive.
Yeah.
Yeah.
And Barbara Finlay, I also know her. She's in visual, isn't she in eye movement or visual attention or something? Yeah. Oh. Yeah, I think this, my immediate reaction is this is great. Of course, we have all terribly filled agendas, but I really think that I'll dig into that. And so the first goal would be to do something that would be good for pre-proposal, which would be also about identifying the why we want to do that, why it's important.
Right. I mean, the way these things work, if we could get a kind of settle in on an outline and do a pre-proposal, we probably have like a year to write the things.
Yeah.
So it wouldn't be something that we would have to dig into immediately, and maybe we can also, if we have a group of us working on it, we can divvy it up, and once you see the forest for the trees, then you can say, all right, yeah, you go off and write this part, you go off and write this part.
Yeah.
Do spend 6 months each just writing different parts, and then put it together in a
Good. And just volunteered to do a presentation in 1 month. So
Oh, great.
that. Yeah. Good. So we should probably call this to a close. Assuming that we would maybe iterate some of the organizational issues in 2 weeks. Seems like they're in Portugal. The prime minister resigned, was thrown out. I just got the message from my son. Yeah, and there are some people who make parties on the street. I mean, they have some political unrest because they're introducing some new taxes and something. I don't know exactly. Yeah, sorry. This was the beeping that you just heard. Good. So I'll follow up some of our social media stuff by sending that email out. And I think we wanted to do the scientific part like every second event, which might be good because we might not have enough time for that. So I'm assuming next week we'll do in 2 weeks we'll do something more organizational, unless somebody tells me something otherwise.
Yeah, that sounds fine. I mean, be happy to we can
what we really should do is talk about these guests again and driving that forward.
Yeah, if we want to pursue that,
that
would be good. Yeah, so maybe we can make that the focus of discussion next time.
Yeah, that would be really good.
Yeah,
and I really appreciate help with that, and you guys are all good for that. Good. Thanks, Aaron, also for joining. Evelina, those from far. Are you in the US, Evelina? Yeah. No, in Europe. Okay, good. Okay.
I'm on the way from Hamburg to Corpus. So.
Okay. Okay. Good. Okay.
Okay.
Good. Good to see you.
Bye bye.
You.
Good discussion.
bye bye.